Welcome back to week 8 of the ma161 calculus. My name is Götz Pfeiffer and this video is about derivatives of trigonometric functions. That's your sine, cosine and tan function. So here's a diagram that contains the graphs of the sine and the cosine functions and their negatives. Looking at these graphs and keeping in mind that the derivative of f of x at a point A is the slope of the graph or the tangent to f of x at A, it's quite tempting to guess that the derivative of the sine function is the cosine function and the derivative of the cosine function is minus sine of x. And that's what they are. We'll justify this later, but for now here's rule number 8, the derivatives of trigonometric functions. And the derivative d over dx of sine of x is cosine x, the derivative d over dx of cosine x is minus the sine of x, and the derivative d over dx tan x is sec x squared, or 1 over the square of the cosine of x. This latter one, like the tan function being the quotient of sine and cosine, is a case for the quotient rule. A quick one, actually. The derivative of the quotient sine x over cosine x by the quotient rule is bottom function cosine times the derivative of the top function of the sine function minus top function times the derivative of the bottom function. Now if we substitute them, the derivative of the sine function is the cosine, so the first term here becomes cosine squared. The derivative of the cosine is minus the sine function, so the second term here, minus sine x, derivative of cosine x, becomes plus sine squared, and by the fundamental trigonometric identity, sine squared plus cosine squared is 1, so all of this simplifies to 1 over cosine squared x, and 1 over cosine, often called the sec function, sec of x, gives the derivative d over dx of tan x as sec squared of x. For sine and cosine we need a bit more work. Actually we'll only do the sine, let's look at examples first. So here, just for illustration purposes, is the graph of tan x that we've seen before with its vertical asymptotes here, and the graph in light blue of its derivative, the sec x squared function, which is always positive, or has these vertical asymptotes as well, and it reflects the slope of the tan function, reflects the fact that the slope of the tan function is always positive. It's sometimes it's steeper than at other times, but it's always positive. Here's a derivative to calculate. Try and differentiate x squared times sine x. Well, this is a product of x squared and sine x, so we can use the product rule to calculate the derivative of this function as first factor times derivative of the second plus second factor times derivative of the first. The derivative of sine is the cosine function, so we get x squared times cosine x, and the derivative of x squared is 2x, so this second term is 2x times sine x. Or the derivative of sine x times cosine x, Again, it's a product, so we can apply the product rule and calculate the derivative of this product as first factor times the derivative of the second plus second factor times derivative of the first, and taking the derivatives into account, and the cosine, the derivative of the cosine is minus sine x, so we get minus sine x squared from here. Derivative of sine x is the cosine, so we get a contribution cosine squared from here, which one can write as cosine squared of x minus sine squared of x. There are some limits which are useful for differentiating the sine function from first principles, but they're also of some interest in their own right. These are the trigonometric limit that we've seen before and estimated at the time to be 1. That's the limit of sine theta over theta as theta goes to 0. It is indeed 1, as we'll see shortly. And the related limit is the limit of cosine theta minus 1 over theta as theta goes to 0. And this limit is 0. For the trigonometric limit, one starts with the observation that by their trigonometric definition, sine theta is always less than or equal theta if theta is chosen in the open interval between 0 and pi over 2. That corresponds to 90 degrees. Sine theta is less than or equal theta, and theta in turn is less than or equal tan theta for these values of theta. These two inequalities can be used to, the first one by dividing by theta, and we choose theta different from 0, so we can divide by theta. Then this inequality turns into sine theta over theta is less than or equal 1. And the other inequality, using the fact that tan theta is sine over cosine of theta, multiplying both sides with the cosine and dividing by theta, we get that the cosine of theta is less than or equal this quotient, sine theta over theta. Effectively, we have now squeezed the sine theta over theta quotient between the constant 1 function on the one side and the cosine theta on the other side. That's what this diagram illustrates. Here in red we have the constant 1, in green we have the cosine function, and in dark blue we have the sine x over x function here in terms of x. And you see that not always, but for x chosen close enough, like in this range between 0 and pi over 2, close enough to 0, the blue graph here is indeed squeezed in between the red line for the constant 1 and the green line for the graph of the cosine. And by the squeeze theorem that we saw at the time, we can now argue that since both the cosine and the constant 1 function have the property that their limits as theta approaches 0 are both 1 or the same, the squeezed in function sine theta over theta has no way out, has no chance but to have this limit 1 as well as theta approaches 0. Now that's a proper calculus argument that establishes this limit, as opposed to the estimates that we went through earlier by looking at values of this quotient for choices of theta near 0. The second of these limits follows from the first as follows. Here using a small trick, multiplying both top and bottom of this quotient by cosine theta plus 1, using the binomial formula of the form a squared minus b squared is a minus b times a plus b. The top then becomes cosine squared theta minus 1, and the bottom theta times cosine theta plus 1. The fundamental trigonometric identity, saying that cosine squared plus sine squared is 1, shows that cosine squared theta minus 1 is sine theta squared, and so we can rewrite this quotient as the product of sine theta over theta and sine theta over cosine theta plus 1, and then applying the limit laws. We already know the limit of this quotient. This is 1. Sine theta goes to 0, cosine theta goes to 1, and 1 goes to 1. We get 1 times 0 over 1 plus 1, which is 0, establishing this limit. I said these limits are sometimes of interest in their own right. Sometimes one is asked to find a limit of the form x goes to 0 of the expression sine 7x over 4x. This is somewhat similar to what we saw there, and the solution here would be to rewrite the limit here as a multiple of sine 7x over 7x, in this case 7 over 4 times this quotient, and then 7x goes to 0 in the same way as x goes to 0, so we can substitute, say, theta for 7x. Using the limit laws, we pull the constant out and get 7 over 4 times the limit as theta goes to 0 sine theta over theta. This is the limit we just established to be 1. So this shows that the limit in question here is 7 over 4. With these limits in place, one can then differentiate sine x from first principles. I leave this again to the end of the video in case you want to skip this, and I'll move forward to one more thing: the multiplicative inverses of sine x, cosine x, and tan x. They're called cotan, as the multiplicative inverse of the tan function is cotan function, cosine x over sine x. The multiplicative inverse of cosine we've seen already appearing in the derivative of the tan function is called the sec of x, and the cosec x, cosecant, is 1 over sine x, and that's the multiplicative inverses, not to be confused with the inverse functions. The derivatives of these functions can be found by the quotient rule. This is something I'd suggest you try yourself. And the interesting fact is that the derivatives of these functions are trigonometric functions, or products of them again. The derivative of the cosine of the cotan is minus the square of the cosec. Derivative of sec of x is sec of x times tan of x, and the derivative of the cosec is minus cosec x times cotan x. And with all these derivatives you can find in the formula books, and you can use them then to differentiate expressions involving trigonometric functions, like this one, sec x over 1 plus tan x. What we're looking at is a quotient, so this is a case for the quotient rule. And according to the quotient rule, the derivative of this expression is top function times the derivative of the bottom function times derivative of the top function minus top function times the derivative of the bottom function divided by the square of the bottom function, and the derivative of sec x is sec x times tan x. Here the derivative of 1 plus tan x is the derivative of tan x, which is sec x squared, and from here one can take one factor sec x out as a common factor, and what remains is tan x plus tan squared x minus sec x squared. And now there's a trigonometric identity, tan squared x plus 1 equals sec squared of x, corresponding to the fundamental trigonometric identity, sine squared plus cosine squared equals 1. And if we apply this here, we can simplify the expression to sec x times tan x minus 1 over 1 plus tan x squared. Now here in the diagram you see the graph of this function, and the horizontal red lines here identify places in this graph where the graph has horizontal asymptotes, that is where the derivative is 0. And this derivative here is, well, sec x we saw earlier is never 0, is always positive. So this derivative is 0 when tan x minus 1 is 0, that is when tan x equals 1, and that's at these places which are various fractional multiples of pi. So that would be it. If you're interested, I'll do the sine x from first principles, the derivative of sine x from first principles. When we set up the difference quotient, and the derivative with respect to x of sine x is the limit as h goes to 0 of sine x plus h minus sine x over h. We need to know what's the sign of this sum of x plus h. Luckily, there's an addition formula for the sign of the sum of two angles, which is described in the formula book as sine x times cosine h plus cosine x times sine h. And if we substitute this in this quotient, we get this longish expression where grouping similar things, like here in this limit, when h goes to 0, x and with that sine x and cosine x really are constant values, and this is for a fixed x. So sine x is fixed and cosine x is fixed. So collecting all the things that go with sine x and then one cosine x, we can rewrite this expression as sine x times cosine h minus 1 over h, where, as I said, sine x is a constant, plus cosine x times sine h over h, where with the limit laws again we can take the constants out, or could regard this limit of a sum as a sum of two limits, and then we can take the constants out, and we find that we're now looking at sine x times a limit that we've just calculated, plus cosine x times a limit we've just calculated. And this limit as h goes to 0 of cosine h minus 1 over h was 0, So that's 0 times the sine x, and this trigonometric limit we know is 1. So overall, this limit, which is the derivative of sine x with respect to x, is cosine x. The derivative of the cosine x can be found in a similar way to be minus sine x, but I'll leave that out, I'll leave that to you. That's the trigonometric functions. And next up is my favorite differentiation rule, the chain rule.